We're continuing with Chapter 5 in the statistics textbook. In this video, we're going to go through section 5.4, which is on percentiles. So in the previous section, in the previous video, if we come here to the previous section, in this paragraph, the textbook gave kind of a side note. It says, "It is a remarkable fact that many histograms follow the normal curve." Okay, so many histograms, you can assume that they're following close to a normal distribution. That's the case for many histograms. Okay, now just remember, when we're saying a histogram, what are we saying? What does that mean? A histogram follows the normal curve. A histogram is just a list of numbers. Behind the histogram, underlying a histogram is a list of numbers, a list of heights, a list of weights, a list of blood pressures, a list of test scores. It's one list of numbers. Okay, so think about it that way as well. When they say histograms, it's saying that it's a remarkable fact that many histograms are just any list of numbers. A list of experimental data. With experimental data, you get different categories of data collected. Each category is its own list of numbers. So many lists of numbers follow the normal curve, or they're normally distributed, is what it's saying. Okay, for such histograms, the average and standard deviation are good summary statistics. If a histogram follows a normal curve, it looks something like the sketch in figure 4. So yeah, that's the idea. Here's a histogram that you can draw a normal curve over it and see that, you can assume that the data is normally distributed. The average pins down the center and the standard deviation gives the spread, okay? That is nearly all there is to say about the histogram if its shape is like the normal curve. All right, so what it's saying here is that if you have a list of numbers that you can make a good assumption that it's normally distributed, the data, then the average and the standard deviation, in that case, the average and the standard deviation are great descriptors of that data. It even goes so far to say that that's all there is to say about that data. If you have normally distributed data, then all a statistician needs is just tell me the average, tell me the standard deviation, and I know everything there is to know about that data. That's pretty much what it's saying here. If its shape is like the normal curve. Okay, but many other histograms, however, do not follow the normal curve, of course. In such cases, the average and standard deviation are poor summary statistics. Interesting. So what this is saying is that if you've got a list of numbers, and this is going to be the case, and you look at that list and it's not normally distributed, you can't assume that it follows a normal distribution. For example, like this, they give an example here, right? You can't say that this is normally distributed, and that's going to happen in a lot of cases, right? But what they're saying here is that in that case, that any list of numbers you can calculate an average and a standard deviation, no matter what the list, any list of numbers. But in the case that it's not normally distributed, then giving someone the average and the standard deviation for that list of numbers, that's a poor summary statistic. Those are poor descriptors for that list of numbers. More about this in the next section. So they're going to address this in section 4 in this video. The average and standard deviation can be used to summarize data following the normal curve. They are less satisfactory for other kinds of data. Take the distribution of family income in the U.S. in 2004, shown in figure 5. So distribution of family income, percent per $1,000. Right, so this many families made $25,000 a year. If you take this width of the block times the height, that percentage of the data points made $25,000 within this range, around $25,000 a year. The average income for the families in figure 5 was about $60,000. All right, so about, I guess in here. The standard deviation was about $40,000. So the normal approximation suggests that about 7% of these families had negative incomes. You see what it's saying here? If you take the average and the standard deviation of this histogram and you apply the normal approximation to that, then the normal approximation would suggest that 7% of the families had negative incomes. What do they mean by that? Because you assume, with the normal distribution, you assume 68% of the data points are within one standard deviation. 95% are within 2. Well, look, if the standard deviation is 40,000, you go 40 below 60, you're at 20,000. You go another 40, you're at minus 20,000, which makes no sense. But you're even minus $10,000 of income is within 2 standard deviations. So you see, it doesn't really make sense. They're illustrating the shortcoming of the average and the standard deviation for a list of numbers that are a histogram that's not distributed normally. The reason for this blunder, the histogram in figure 5 does not follow the normal curve at all well. It has a long right-hand tail. To summarize such histograms, statisticians often use percentiles. Okay, so that's interesting. If you have a histogram that you can assume is normally distributed, a list of numbers, then the average and the standard deviation are great to present to somebody, right? If you're going to make a presentation or you're going to try and convince someone of something, the average and the standard deviation are great descriptors. But if it's not normally distributed, you need to resort to something else that can describe that data. I mean, you can still use the average. I mean, the average would still be a good descriptor, I guess, in any situation. But the standard deviation, you could potentially use that as well. But you can see how it's not as powerful if the data isn't normally distributed. But what it's saying is, in those cases, you can use percentiles instead. And we'll see, you can use percentiles with a normal distribution as well. But this could be really powerful if the data isn't normally distributed. So what is a percentile? Okay, so here's the percentiles for this histogram here, family income levels in the U.S. Okay, here's the first percentile, here's the 10th percentile, here's the 25th percentile, 50th, etc. The first percentile of the income distribution was $0, meaning that about 1% of the families had incomes of $0 or less, and about 99% had incomes above that level. Mainly the families with no income were retired or not working for some other reason. The 10th percentile was $15,000. So about 10% of the families had incomes below that level, and 90% were above. Okay, so what is it saying here? If we come to the histogram, okay, what percentile is doing is you imagine you've got a histogram and you start at the origin. You start at the left side of the horizontal axis. Start here. Okay, and you're going to make your way up. Okay, so you're traveling up, and then all of a sudden when you get to a point where the area on the graph behind that point is, let's say, 10%, then that value on the horizontal axis is called the 10th percentile. This is kind of confusing because you think percentile, you think that means percent. Percentile doesn't, percentile is in whatever the horizontal axis is. So the 10th percentile is going to be $15,000. It's not percent. So the 10th percentile of the income distribution is $15,000. Okay, so 15 would be about, I guess we're doing somewhere in here. So you're traveling, all of a sudden, boom, there's behind a vertical line behind this point is 10% of the graph. This number, which would be about 15, that's the 10th percentile. And how do you interpret that? That means that 10% of the families in America, or whatever the histogram means, had an income below $15,000. Or you could say it the other way. 90% of the families in America in 2004 had income above $15,000. You see? All right, let's do the 25th percentile. You start here at the origin. You're going. Boom. Stop. You stop. Why did you stop? Because the percentage, if you draw a vertical line from that point, the percentage of the area of the histogram behind that vertical line, is that a percentile you're looking for? The 25th percentile. The 25th percentile is $29,000. Is that what it says? Let me make sure. Yeah, 25th percentile is $29,000. Okay, so 25% of the families in the U.S. in 2004 had income below $29,000. 75% had income above $29,000 per year. Okay, now it says the first percentile is $0. So what they're saying there is like, you just get to like here. And I guess they just rounded down to 0. You get the idea. I mean, maybe even a lot of times the entire histogram, the visual area of the histogram is not even 100%. It's like 99.95%, right? So maybe we can't even see what actually is 1%. But you get the idea. Okay, now what's the 50th percentile? Pause the video. You should, if you've been following in the course up to this point, you should be able to answer this. What is the 50th percentile going to be? What number are we going to land on? Don't say the average. Don't say the average. What is the point on a histogram where 50% of at that point on the horizontal axis, 50% of the area of the histogram is to the left and 50% of the area in the histogram is to the right? That can be the average in certain circumstances if the histogram is symmetric. But particularly in this section, we're not dealing with symmetric histograms. So, but no matter what the situation, at what point on the x-axis is, when you draw a vertical line from that point, 50% of the area is to the left and 50% of the area on the histogram is to the right. That's the median. Okay, and that's it says 54,000. So you're walking up. All of a sudden you get to like here, this vertical line, 50% of the data of the area is to the left, 50% to the right. That's the 50th percentile, whatever this number is in horizontal units, $54,000, whatever it was. Okay, pretty cool, right? Now, as you can imagine, you can absolutely apply this with with data that's normally distributed as well. That's what we're going to do in the next section. All right, by definition, the interquartile range means the 75th percentile minus the 25th percentile. And these are not percents. So this is going to be whatever the horizontal axis unit of the histogram is. So this would be, for this case, it would be income in thousands of dollars. And we talked about this in chapter 4, that there are different ways of describing the center point of a histogram or a list of numbers, the average or the median. There's different ways of describing the spread. One is a standard deviation, and another is the interquartile range. And why is this potentially valuable? Because we just saw a few minutes ago that the standard deviation was like giving negative numbers. If you went plus or minus 2 standard deviations, you're getting a negative income, right? And so but you don't. 2 standard deviations is not that far away from the average. It's far, but not that far. So in certain cases, you might want to use the interquartile range, which is the 75th percentile minus the 25th percentile. But again, a normal distribution it has an interquartile range as well, no problem. But this is just another option that represents spread for a list of numbers. This is sometimes used as a measure of spread when the distribution has a long tail. For example, the interquartile range for table 1 is 75th percentile minus the 25th percentile. 90,000 minus 29,000 is $61,000. For reasons of their own, statisticians call the de Moivre's curve normal. Yeah, the normal curve. The de Moivre created it. We saw at the beginning of this chapter. This gives the impression that other curves are abnormal. Not so. Many histograms follow the normal curve very well, and many others, like the income histogram, do not. Later in the book, we will present a mathematical theory which helps explain when histograms should follow the normal curve. All right, so that's important to note. It has the name normal. The normal curve has the name normal, but don't let that make you think that other curves are like out of the ordinary, because it says many curves follow the normal curve very well, but many others don't. And that makes sense. All right, let's go ahead and work the example problems in this section. Fill in the blanks using the options below. The percentage of families in Table 1 with incomes below $90,000 was about what? The percentage of families in Table 1 with incomes below $90,000. Well, what's the percent? What percentile is this? That's the 75th percentile. Okay, so yeah, that's one thing I want to mention. Let's come back here to the income table. So, here's 90,000 about, right? Just to make this clear, I mentioned you start at the origin and you walk up. You get to this point, okay? $90,000. So that means that it was 75%, was it? That's the 75th percentile? Yeah. So 75% of the area is behind this line. That's the 75th percentile. Or you could look at it like 25% or above this value. But note that I want to make it clear when it comes to actually the name of the name percentile, when you're characterizing something as this is this percentile, you're never going to say the fact that 25% of the data points are above this line. Has nothing to do with the name percentile. As far as the naming convention, if you hear 75th percentile and you're given a weight or a income or a height, then that means 75% of the data points were below that value, right? So you're thinking below. You first think below. Then if you want to go ahead and say, okay, well, that means correspondingly that 25% were above that value, then you can go ahead and do that. But the name, when you're thinking about when you hear on TV, the 20th percentile, the 10th percentile, the whatever, 99th percentile, then that percent, the 99th percentile, that percent of data points were below the value they gave you for the percentile. Just want to make that clear. So the percentage of families in Table 1 with incomes below $90,000 was 75%. About 25% of the families in Table 1 had incomes below what? What's the 25th percentile? $29,000. The percentage of families in Table 1 with incomes between $15,000 and $125,000 was about what? Okay, so if we come here, we can look and see what's the percentage between 15 and 135. That'll give us an idea. And so what we can think about is that if 10% were below 15 and 90% was below 135, then you'd have 80% in between. So it'd be a little bit under 80%. 75% is the best option here. In 2004, a family with an income of $9,000 was at the what percentile of the income distribution? Okay, so it gives us options here. Well, this is not going to be 95. It's going to be the 5th percentile. It's definitely not going to be 95, so it has to be 5th. It's going to be a low percentile. Why is it going to be low? Because what percentage of all of the data points had incomes below $9,000 a year? That's not going to be a lot. Well, a family that made $174,000 was that's going to be higher. I guess, I don't know if it'd be 95, but it's definitely not going to be 5, so it'd be 95. Let's come to the table. 174. So that looks about to be, there's 95% of the area below this. Is the 25th percentile for the distribution of family income in 1973 around 7,000, 10,000, or 25,000? See Table 1 on page 35. Okay, here's Table 1. Now, what is the question? Is the 25th percentile, what does the 25th percentile mean? What X value on the horizontal axis corresponds to there's 25% of the histogram area below that value. Okay, so how could this is not percentile here. Okay, this is actually the percent of data points in that interval. So what we can do is, if you think about it, if 1% of the data points are within this block, 2% are within this block, 3% are within this block, then to the left, once we go right past this income level, once right at $3,000, at $3,000, $3,000 is going to be the 3, 4, 5, the 6th percentile. You see, so 3, 4, 5, 6, 10, 15, 20, 25. So $7,000 is going to be the 25th percentile. So 7,000. Skin fold thickness is used to measure body fat. A histogram for skin fold thickness is shown below. The units on the horizontal axis are millimeters. The 25th percentile of skin fold thickness is what? But they put a 25 here. Wait, what? The 25th percentile would be, so if Looks like the average of the median is somewhere in here. So the 25th percentile would be kind of over here, around 10-ish. Wait, what is, okay, so these are the options. It looks like 25 is the 50th percentile. That looks to be about the median. So are we going to use quite a bit smaller than, around, or quite a bit bigger than? Quite a bit smaller than. Not around. Around would be, you know, somewhere like here. No, it's going to be all the way over here. Quite a bit smaller than 25 millimeters. Can this be determined from the figure? No. I mean, unless, well, you could if this was, they told us this is drawn to like a scale, like almost exactly, you could use Photoshop and find the median. Use Photoshop and find out what position, what is there to high precision, what's 50% area to the left, 50% to the right, and then cut that in half. Cut that area to the left of the median in half, and that would be the fit. I mean, no, there's not enough information because this isn't drawn to scale. I mean, I don't think. A histogram is sketched below. How is it different from the normal curve? Is the interquartile range around 15, 25, or 50? All right. Well, how is it different from the normal curve? It looks less spread out. Normal curve looks more like, so it looks like the standard deviation is less, but the average is the same. I mean, it's not drawn to standard units, right? But like you could convert this to standard units and it looks like a normal curve with a smaller standard deviation. But actually, and also it has these tails are bigger too. The normal curve is like, so the tails are larger. Is the interquartile range around 15, 25, or 50? So the interquartile range, the 25th percentile. So, all right, this is kind of difficult. So we need to cut this area in half. It doesn't mean, and it's not going to be the middle. Like we're not going to go to 25 for sure. That's not cutting the area in half. We would come to like, almost like here. Right now, so that's the 25th percentile, and then the 75th percentile would be here, right? So you see what I'm doing? Like if you add up this area, that should be equal to this area. All right. So what is that about? Looks like 55 minus 45. So about 10, 15, about 15. Okay, now in the next section, we're just going to apply percentiles to the normal curve. Easy. If you want to use percentiles to describe something that's normally distributed, you can.